Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Scientific curiosity often leads to surprising discoveries. Flexible solar cells are comprised of ceramic layers deposited on a polymeric substrate. Although the ceramic is expected to crack when the solar cell flexes, it has always been assumed that the substrate, with its excellent toughness, remains intact. Over time, this cracking causes the efficiency of the solar cell to degrade, but new research has shown that the polymer also cracks, and mitigating the cracking of the polymer inhibits degradation of solar cell efficiency.
People say that you have solved a problem that people didn't know they had. They didn't know the substrate cracked, but then now you fixed it.
That was Nitin Padture, who is the Otis E. Randall University professor and the founding director of the Initiative for Sustainable Energy at Brown University. It was the curiosity of one graduate student that uncovered the cracks in the substrate, which was coated with only a transparent conducting oxide thin film. The cracks were initially seen after focused ion beam milling was used to create a hole in the thin film, and then confirmed when etching was used to remove the thin film. The degradation in the electronic properties is thought to be caused by debris in the cracks preventing closure after the device has been flexed. Preventing the cracking then limits this degradation mechanism.
It was amazing, the resourcefulness and the creativity students demonstrate. Like, tried something different that people have not tried. And so that leads to all these things, and that's inspiring.
Modelling originally published in the 1970s suggested that elastic mismatch caused the polymeric substrate to crack.
After you understand the model, it makes sense in hindsight. Of course, that's exactly what's going to happen. But it is exciting to see something that I didn't expect. That's all research is about, is that you find something unexpected and you figure out why it is happening. And then as an engineer, we go one step beyond that and say, okay, well, now we understand this. So how do we fix it?
To mitigate the cracking, an interlayer was incorporated. In a proof of concept device, polymethyl methacrylate was deposited on a polyethylene naphthalene substrate using spin coating, and an indium zinc oxide layer was then deposited using sputtering. The stiffness of the interlayer relative to the other layers is important for arresting crack propagation. A map of the elastic mismatch between the top and bottom layers was created, and areas on the map were identified for crack mitigation.
If you just use the elastic modulus as the criterion, that's not enough because the mechanics are more complicated. It has to be the elastic mismatch parameters, which contain other constants of the different materials.
The interlayer doesn't affect the properties of the solar cell, as it's transparent to light and deposited below the conducting layer. The thickness is critical, as it needs to be thick enough to mitigate cracking but retain its transparency. This means that the mitigation technique has applications beyond solar cells. It could be used for photochromics, touchscreens, and foldable displays. Tests over thousands of cycles showed that the inclusion of an interlayer prevented the change in resistance that would usually signal that cracking had caused the electronic properties to degrade. The research can now move on to look at how to build a full stack to see how a complete device performs when deposited on top of the interlayer. This work was published in a recent issue of NPJ Flexible Electronics. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.